Homework 12, 6.2, Combinations in the Binomial Distribution, Video 4. In order to answer the question posed at the end of the last video, we need to look at what's called the binomial probability formula, and it goes something like this. Suppose you have a binomial experiment with n trials, and the probability of a success is p. So over here, 10 trials, probability of a success is 25%, or 0.25. Let capital X be a random variable that counts the number of successes out of n trials. So you guess at the 10 questions, and capital X is how many of them you got correct. Then the probability of lowercase x successes, so little x is going to represent the number of successes we're looking for. In this case, 7 or more, but we'll start with just 7. Then the probability of x successes is, in other words, the probability of the capital X equals the number of successes, is a combination NCX, so number of trials, combination, number of successes, times p to the x, the probability of success raised to the power that equals the number of successes, times 1 minus p to the n minus x power. 1 minus p represents the probability of a failure. This exponent represents the number of failures. Remember, this is how many trials, this is how many successes, so the difference would be the number of failures. Why is the combination here? A little beyond what we can talk about now, especially since we skipped section 5.4. But let's go back to the question about passing the test. And I know to pass it you have to get 7 or more correct, but let's just focus on 7 for a moment. So in the previous example, we had n equals 10, and p is equal to 0.25. So if we want to know the probability that capital X is equal to 7, remember, X is counting the number of successes, so this is saying the probability that the number of successes is 7, so we successfully answered 7 questions, would be n, which is the number of trials, so 10, combinations, capital C, little x, which is the number of successes, 10C7, we've already figured that out in the previous video, times the probability of a success, which is 0.25, raised to the power that matches the number of successes. So 25% of the time we're going to get a success and we want to get 7 of them. And in parentheses, 1 minus p, or equivalently the probability of a failure. If there's a 25% chance that we guess correctly, then there's a 75% chance that we guess incorrectly. So 0.75 is 1 minus p. And the exponent is n minus x, which is just the difference of these two values. It's 3. But contextually, it's the number of failures. If we guess 7 correct, we guess 3 incorrect. And then we just get out a calculator and do the work. Now keep in mind that we already calculated 10C3 in the previous example, and it was 120. But most of the time you'll need to calculate that manually. So let's go ahead and write 120 times 0.5 to the 7 times 0.75 to the third. And then this is just straight up stick it in the calculator and see what happens. All right, 120 times 0.25 exponent 7 times 0.75 exponent 3 equals, that's a very, very, very small number. 0.00, we'll take it to 4 decimal places. 0.0031 when we round it off. So as a percent, 0.31% of the time. So there's not even a 1% chance that if you guess 10 questions at random, you're going to get 7 of them correct. But the question actually asked, what's the probability of getting 7 or more correct? This is only the probability of getting 7 correct. How do we calculate the probability of 7 or more? Well, we know the probability of 7. We could calculate the probability we get 8 correct, and then the probability that we get 9 correct, and then the probability that we get 10 correct. Those are mutually exclusive events, meaning you can't get 7 correct and at the same time get 8 correct, which means that we can find the probability of 7 or 8 or 9 or 10 by simply adding their individual probabilities. So in the next video, we'll look to see how to answer a question like, what's the probability x is greater than or equal to 7, but I just laid it out.